A very good afternoon to all of you and a very happy Makar Sankranti. In Mumbai, we don't feel winter much, but because of heavy urbanization and heavy pollution, and also because of the proximity to the sea. But in the rest of the India, where the cold is bitter, we celebrate the Makar Sankranti or the movement of sun towards the northern hemisphere that brings lots of heat, energy, and relieves people from bitter winter. So it's a festival of rejoice. I hope wherever you are celebrating it. So wishing you a very, very happy Makar Sankranti. Going ahead, remember in this course we are talking about sound. We are having a reference book, Science of Sound by Rossing, and we are in chapter 5. My today's lecture is going to be a rather short lecture because I am concluding my chapter 5. So few topics are remaining. I will conclude them, maybe take up a couple of problems, and instead of starting a new lecture or new class, we might finish little early. We'll gather on a Google Meet if you have any doubts or discussion, and I will share the attendance link on the WhatsApp itself. So just for that, you don't have to join the Google Meet. So in this lecture, we are going to talk about something which is interesting: binaural hearing and localization, and decibel scale. We have already spoken of decibel scale, but more than decibel scale, I want to talk about in general about use of logarithms in sound and hearing. So we'll talk a bit about that and then take up some problems and review at the end. Is there any volume issue? My settings are usual. I hope you can hear me clearly. Please check your system volume, Simran. Please let me know if the volume issue is there. So going ahead, we know that. Good afternoon, Kunika. I hope you all can hear me. Fair enough. So that means my side the volume is going great. From your side, few of you might have some issue with system volume. Please check that. Thank you. Thank you, Siddharth. Thank you, Darren. Thank you, Gomer. Yeah. So let's go ahead. So we all know that we can find directions of the source of sound just by listening to it. We have plenty of examples. So if you have different rooms in your home and somebody calls you, then you know that from which room or which side the sound is coming. If you're walking on the road, if a sound is coming from the front or if it is coming from the behind, again you can localize it easily. If you are in a theater, there are virtual sounds, I mean the virtual surround sounds, where a car moves from right to left again the directions you can make out. So we have this ability to sense the direction of the sound. So in this part of the lecture, we are going to discuss that. So at higher frequencies, what happens is the head casts a shadow. So for example, if you are, if this is your head, this is the model of your head, top view, you can take it as a circle or an ellipse, something like that. And if this is the source of sound, then the sound hits on this side first, while this becomes a shadow part. So the sound intensity on this side drops considerably than this. So this ear receives a sound which is very loud, while this ear receives a sound which is not so loud. Experiment shows that if you are 10,000 hertz or something, then the difference between them is up to around 30 decibel, which is a huge difference. Remember, it's on a logarithmic scale. And therefore, the ear where the sound received is louder, the brain decodes that as towards the source of the sound, while the other ear, which is not receiving that loud sound, the brain decodes that it is away, and that is the way it actually figures out. So depending on how the source moves, if the source moves on to this side, the shadow becomes deeper and the difference becomes more pronounced. If the source goes in the front, then almost the two ears will receive the same sound, and it will be very difficult for human ear to have differential in the sound intensity. So the brain decodes that the sound is in front. In fact, if the sound is behind source of sound, then it is again geometrically the same intensity reaching the two ear, and it is very difficult for the ear to say that it is on left or right. It always say that it is behind. So you can see that if the source is behind or if the source is in front, say at some equal distance, the ear will receive the same intensity. Then how does it define, how does it decide that it is, if it is front or if it is behind? Think over it. I will answer this question maybe a little later. But if the source is at an angle, then the difference in the intensity gives us a hint that source is somewhere in this direction. However, this has been observed at a higher frequencies only. As the frequencies drop, the wavelength increases. These lines are drawn as wavelengths. So as the wavelength increases, here the wavelength is very small compared to the size of the head. If the wavelength increases in size, then a situation comes where the wavelength of the sound wave is almost equivalent or almost on par with the size of the head, human head. And at that time, the diffraction takes place and the diffraction effect becomes more dominant. This acts like a what you have uh, already studied, a cylindrical obstacle to the waves. So as the waves arrive to this cylindrical obstacle, they will turn around. So once they turn around, this ear also, which was in a shadow region at a higher frequency, this ear will also receive a very strong loud frequency. So the difference in the sound intensity of the two ears drop considerably, and then it becomes very difficult to localize. So if you are at a frequency less than 1000 hertz, then the difference in the sound intensity drops to 8 dB or below, and then it becomes really challenging to figure out by just by intensity that from which direction the sound is coming. But another phenomena happens which is responsible for localization, sound localization at a low frequency, and that phenomena is something called as the phase difference. The sound, even though the sound turns around and reaches to this ear, it will reach to this ear at a little later time than compared to this ear. This ear is closer to the ear source, so the sound reaches first. This ear is away from the source, the sound reaches later, and therefore there is a slight difference. And this slight difference in time, which results in the slight difference in the phase of the two waves, would let us enable the difference in the two waves and hence localize the source of the sound. So if your frequency is less than 1000 hertz, this phase difference or the time difference in the two waves reaching to different ears is responsible for localization. If the frequency is more than 3000 hertz or 4000 hertz, it is the audible this difference 30 dB difference that allows you to sense or localize the direction of sound. However, if you are in between the two, if you are in between the two, then there is a confusion. So for example, at 2000 hertz, localizing sound becomes more challenging because both the phenomena do operate. So there is a shadow zone, there is a diffraction, and it's a mix of the two is happening. Overlap is not very sharp. Lot of experiments have revealed that at around 3000 hertz we are least accurate in determining the localization of sound or the source of sound or the direction of sound. It becomes very difficult. This fact that at 3000 hertz it's very difficult to localize the sound can be useful too. For example, in some cases, the source of sound wants to hide itself, and that fact can be used at 3000 hertz. So, finally, what gives us a distinguish between back and front sound? So, it is actually the pinna. Remember the outer structure of the outer ear which protrudes out of the head that gives the distinguishing ability to distinguish between the back and front sound. A sound coming from the front will reach both the ears simultaneously, so no phase lag. It will have same intensity, so there is no intensity difference between left and right ear, but it will be more intense than a similar sound which is coming from the rear at the same distance because of the pinna. The pinna concentrates the amount of sound which is coming from the front and then send it to the ear, which does not do to the sound which is coming from behind. Now, some animals, as we have already discussed, like dog, rabbit, etc., they have a movable pinna, so they can erect their pinna when they are at danger, when they are alert, and they can hear more sharply. We humans don't have that ability, but we have the ability to turn the head. Our neck allows us to turn the head left or right. So even if the sound is coming at an angle, we can turn our head towards that side and convert it into a front sound. So that ability is there with us. So going ahead, logarithmic scale, lot of our hearing involves logarithmic calculation. So where exactly does it come from? So remember in the last class we did talk about critical bands. We did talk about frequencies, different frequencies being heard at different distances. And we also talked about one important fact that if you shift on the basilar membrane, if you shift by an equal distance delta x, then the frequency response actually get doubled. So that phenomena is typically referred as Feckner's law. He worked a lot on sound stimuli and its perception in the 19th century, came up with a wonderful book in 1860. What we call this law as this, the statement could be this, that as stimuli are increased by multiplication, the sensation increase by addition. So if you double the, now this extends that logic of basilar membrane to the other phenomena also. So for example, if you double the intensity of the source, if you double the intensity of the sound source, that is your stimuli, then your sensation will increase by addition. So when you say, I say double, when you multiply by 2 or multiply by 4 or multiply by 8 or multiply by 10, your sensation will add by some value, maybe one step at a time, 1 to 2 to 3 to 4, etc. And the classic example is, as the intensity of sound is doubled, intensity of sound, remember, is the actual intensity from the source. Loudness is the loudness that we perceive. They are two different things. The loudness increased by one step on a scale. So on the scale, if we imagine a scale on which we can perceive the loudness, we will increase it by a step, while the intensity of sound every time when it gets doubled. Mathematicians call these relationships as logarithmic, and that is why logarithmic relationships are everywhere in the study of sound. I give you some more examples of the use of logarithms. So decibel scale is used to express such things such as sound level and amplifier gain are based on logarithms. Frequency response of any audio device like ear or anything else, speaker, etc., is generally written in the term of a logarithmic scale. Keyboards on a piano. So you all are familiar with the piano. If you have not played and if you don't have a piano, just download a piano app and try to play with it. Try to figure out with another frequency app, you can find out what frequency it is playing. Now you on a piano app, your fingers move on keys which are equidistant. They change their position by equal distance in the space. But the frequency does not increase linearly. Frequency increase in some ratio, which is logarithmic. Musical scale itself is logarithmic. So everywhere sound, whichever section you want to study, whether you want to study the basilar membrane and ear sensitivity, you want to study the amplifier, frequency spectrum, musical instruments, or the musical scale themselves, everywhere you will find the use of logarithms, because it is basically inbuilt in human physiology. Every time stimuli is increasing by multiplication, its sensation increases by addition. So that's a very important concept that drives lots of our calculations. This is a logarithmic graph paper. Basically, it is a semi-log graph paper. So this scale is logarithmic. So numbers are not logarithmic, remember, but the scale itself is logarithmic. So advantage is that you don't have to take log to plot on this. You can take your numbers, plot on this, and it will be plotted in the logarithmic fashion. On this side, it is not logarithmic. So equal distances have equal values. So from here to here, if it is, the difference is 5, 10 minus 5. Then from here to here, difference is again 15 minus 10, so 5. Here to here, difference is 20 minus 15, so 5. So every time you move the same physical distance on this scale, your difference in the value is 5. So this is a linear scale. This is the scale you have been designing and using all throughout up till now in your graph plotting. But this side is logarithmic. So look at some example. I go from um, I look at some distance somewhere. So I look at a distance, say from here to say up to 500. So I'm looking at this distance. Now this distance, you can see that the difference is 500 minus 100, which is 400. Okay. Now elsewhere, look at a similar distance. So if you take a similar distance, then it is here from this line to this line. This has the same distance as from here to here. Now look at this difference. This is 5000 minus 1000. So from here to here, the difference is 4000, while from here to here, difference is only 400. So you are moving by the same amount, same physical space on this axis at two different locations, but your values differ considerably. So what this graph paper does is that it takes the log of your values and plots them on the x-axis, while y-axis is still linear. So most of the frequency responses are plotted on these kind of graph papers. So suppose if you have to find the frequency response of a speaker, what all frequencies the speaker can produce, then plot all the frequencies here, because frequency range could be enormous from 20 hertz to 20,000 hertz. Plotting them linearly on a scale is very challenging, not possible. Or even if it's possible, the accuracy won't be great. So you take a log. The moment you take the log, the scale compresses and you can plot it easily. This is called semi-log paper. Why semi-log? Because only one axis is logarithmic, not the other one. So use of logarithm is everywhere, as we have seen. So next chapter, I'm going to again talk about decimal scale in little detail. We have already talked about it in the revision. So it will again revision of revision. But with this discussion, we finished chapter 5. Let me take some of the review questions. I have my first question. If any one of you wants to answer by typing it back very briefly, you can try. If everyone's hearing sensitivity were reduced by 10 dB, in what ways would our lives probably be different? So think about this answer. If you're thinking about this answer, please don't think about 10 dB much. Just imagine that your hearing sensitivity is reduced suddenly by some considerable amount. What will happen? So can anyone write a line or two? Localization problem. Yes, sound localization would become problematic, of course, because remember that localization depends on the difference. That will also drop. So localizing sound will be challenging. Very soft tones or very feeble sound in our surrounding will be unheard. So for example, fan noise, which is little subdued, will not be heard at all. If you're in an air conditioned car traveling, sound coming out from outside will not be heard. Maybe you may not be hear the horn of another car which could be very close to you. But most important difference that I feel will happen is that everybody will have to shout louder for communication. I am talking to you and you cannot hear me, your sensitivity has gone down. So I have to shout aloud. So if you remember, I mean, if you have noticed, I don't know if you all, but people generally who has kind of a hearing impairedness where by which they hear sounds feeble, I mean their sensitivity has gone down, they tend to talk very loud because for them that becomes the normal voice while we feel that person is shouting. Doctor won't be able to hear heartbeat. That's right. Yeah, that's right, Nimishka. The doctors won't be able to hear the heartbeat, or the stethoscope may require a greater amplification. Normal conversation, yes, Pranav, would be challenging. People have to shout aloud, so that will also become a problem. Now, yeah, so many cases you can think more. There are more review problems in the reference book. Go through them. They will be the part of examination. I'm taking two numerical problems here. I will try to solve them at a different app. So let me move to that app now. So yeah, here it is. So this is my first problem. You can read it. Assume that the outer ear canal is cylindrical pipe 3 centimeter long, closed at one end by the eardrum. Calculate the resonant frequency of this pipe. Our hearing should be specially sensitive for the frequencies near this resonance. So remember I already spoke earlier that the physics deals with model making. So we try to make models, ideal model of various objects, subjects under study. So here the ear canal is a tapering canal, but we can still model it as a cylindrical pipe 3 centimeter long. So if you have pen and paper around you, just try to solve this. So you have this is 3 centimeter long pipe tube, and remember the inside you will get an ear drum. So it is a tube which is closed completely. So on this side it is closed, on this side is open, length is 3 centimeter. So what exactly is going to be the velocity or the frequency? So we are all familiar with the problem. The frequency of vibration of a tube which is closed at one end is in is odd integral multiples of V by 4L. Do remember odd integral. Now here we are looking at the fundamental, so I'm going to use 1 as my multiple. So this is easy problem to solve. I can simply put the values. V is, if it's not provided, you take it as 340. If it's provided, then use that value. 340 meter per second divided by 4 and divided by 3 centimeter, remember. So I will use it as 3 into 10 power minus 2 meter. So you can easily solve this. I mean, this is easy. So if you solve this, I have already solved it for you. You get 2830 hertz. So that is your frequency. Remember, this is close to 3000. So for talking purpose, you call it 3000. So around 3000 hertz, maybe as you hit around 2500 to 3000, the sensitivity of the eardrum increases. And even if the original sound intensity remains the same, the the ear cavity starts vibrating in resonance and absorbs more sound and sound louder. So at this frequencies sound louder. Remember that part. So that becomes one question. The other question is calculate the difference in the arrival time at the 2 years for a sound that comes from 45-degree direction from the northwest. For example, when the listener faces north. So I have to calculate the arrival time, as I said, at lower frequencies. Let us revise. At higher frequencies, it is the shadow, it is the change in the intensity between the 2 years which helps localization. But if the frequencies are lower, then the diffraction takes place and the intensity difference drops, but the phase difference is always there, which happens because the sound reaches to the farther ear little delayed. How much delayed? That depends on the direction of sound. So here is a problem which gives us opportunity to calculate that delay. So let us try to do that. So all I can do is I can make the model of the head, so which is slightly, let's say, oval in nature. So yes, it is here. I can draw the 2 ears, one on this side and one on this side. Not bad. Computer drawing skills are improving. Teachers are subjected to so many new skills and learning this semester that we had been not in past many years. I mean, learning was always there, but learning was always very slow paced. But this year we were forced to learn, upgrade, change at a very rapid pace. And many of us may not like to go back to the old system. But anyway, so this is my line of the line joining the 2 ears. The problem says that this guy is facing north. So this is my north. And the sound comes from a 45-degree direction. The sound is coming somewhere from this side. Let's say the sound is coming from far. So the sound will reach to this ear to from a 45-degree direction, and again from this ear from a 45-degree direction. Well, remember, I assume that the sound is a point source of sound and it is far. So these two lines, although they appear to be parallel, they are actually not parallel, slightly tapering, and eventually they will meet at a point. But what it says is that this angle is 45, say for 1. The source is at such a distance that I can take this angle to be 45 for both the ear. And that is a very important assumption in this problem. That for both the ears, the angle is 45. Do remember this. So how much late does this ear receive the sound? So in order to find that, I can always drop a perpendicular from here to the other ray, say this way, a perpendicular, remember, this is 90-degree. So now this is the path difference that I have to find. The path difference in the two waves, this is the extra distance that the wave is traveling, which I'm showing in red color. Okay, so how do we go about it? So for this to do, you know that this angle you are familiar with, you want to know this distance, but you must know one more information. The other information is the distance between the 2 ears. So, I mean, you can figure out what is the distance between 2 ears. I will take a tentative figure here, maybe of many of you must be watching it on mobile, so maybe zooming will help you to see the diagram. This is the path difference which I want to calculate. This angle is 45, which is same as this one. This distance between the 2 ears, I can take it as around 17 centimeter. Ask somebody at your home to help you to find out this distance. It might be same, plus minus 1.11 or 2 centimeters here and there. If you have particularly large head with more gray matter, then you will have more separation. Those who have less separation, don't get disheartened that your gray matter will be less. It will not be. So yeah, so going ahead, let me use some scale 100 so that yeah, everything is visible. So now I want to find out, this is angle is 45, this is 17. So I can use, this is adjacent side. Let me say that this side is x. So now I can solve a simple trigonometric ratio. I can say that cos 45 is side adjacent. Side adjacent is x upon hypotenuse, which is, I can leave it 17 and my answer will remain in centimeter. So x is equal to 17. What is cos 45? 0.7, 1 by root 2, remember, but which is 0.707. So I will make it, I will simply write it as 0.707, and if I solve it, I will get approximately this answer as 12 centimeter. So look at it. In order to travel to other ear, the sound takes a distance of 12 centimeter more. So how much time will it take extra? So you know velocity is distance upon time. So time is distance upon velocity. So I can solve that part quickly now. T is equal to distance upon velocity, but distance is 12 centimeter. I can convert it into meter. So this becomes 12 divided by 340. And once I solve this part, what I get is 0.35 millisecond. So this becomes your answer. Your delay is 0.35 millisecond. The human ear can calculate, brain can calculate that delay and then figure out what is the distance or what is the direction in which the sound is coming. So that's very fascinating. 24.04, ये कहाँ से आया भाई? Maybe I can talk about this figure after the class. So yeah, this was the last thing that we had to do today in this chapter. We finished this chapter. Since the entire class is here, I would like to tell you that please check your Canvas account. I have posted the baseline test for Saturday 5 o'clock, 5 to 5:30 on Canvas. Please study and attempt that. If it is not visible on your Canvas account, then you can come to Google Meet that I'm going to create immediately after this class and speak to me there on that. With this, A, we finish this chapter, B, we end this lecture.